This video is brought to you by mywayteaching.com.
Now let us study the collision in one dimension. See, consider the completely inelastic collision, which means a collision in which the two particles move together after the collision. So in that case, theta 1 is equal to theta 2, as we saw in the previous figure, that is equal to 0. Momentum is conserved, which means m1 v1 the initial velocity, is equal to m1 plus m2 final velocity vf. So we can write vf as m1 plus m2 into v1 So the loss in kinetic energy on collision is given by delta k, isn't it? So that we can write it as half m v1 square minus half, that is final velocity m1 m2 into vf is the final velocity. That can be written as half m v1 whole square minus 1 by 2 m1 square vf. You just substitute the value of this vf in this second equation, so we'll get m1 plus m2 square, this is also square, and this one m1 plus m2. So we can write it as half m v1 square minus this one and this one get cancels, half m1 square by m1 plus m2, isn't it? If you take the LCM, and we already know v1 if you further simplify this, we'll get half m1 m2 m1 plus m2 v1 square. Okay, which is a positive quantity. So now let us, this is the first case, let us consider the elastic collision. So using the nomenclature with theta 1 is equal to theta 2 is equal to 0, the momentum and kinetic energy conservation equations, we can again write it as like this: m1 v1 is equal to m1 v1f plus m2 v2f. Okay, that is momentum, and if you consider this kinetic energy, then m1 v1 I square is equal to m1 v1f square plus m2 v2f square. Okay, from these two equations we can write it as m1 v1 I v2f minus v1I m1 v1f v2f minus v1f. Okay, or we can write it as v2f is equal to v2f into v1I minus v1f, that is equal to v1I square minus v1f square. Okay, so at the final output v1I v2f is equal to v1I plus v1f. Okay, so if you substitute this in the equation 3, okay, then we get v1f is equal to m1 plus f2 m1 v1f is equal to m1 minus m2 divided by m1 plus m2 v1I, and v2f is equal to 2 m1 v1I by m1 plus m2. Okay, if you now let us consider two simple cases. In that first cases, if two masses are equal, then if m1 and m2 are equal, then v1f in the first case it will become what? 0, and this in the second v2f will become v2 v1I. Okay, okay, the heavier mass is undistributed while the lighter mass reverses its velocity. So now let us consider a simple problem. slowing down of neutrons. In a nuclear reactor, a neutron of high speed, that is 107 meter per second, must be slowed down to 10 raised to 3 meter per second so that it can have a high probability of interacting with isotope U3592 and causing it to fission. So, show that a neutron can lose most of its kinetic energy in an elastic collision with a light nuclei like deuterium or carbon, which has a mass of only few times the neutron mass. The material making up the light nuclei usually is heavy water, that is D2O, or graphite, that is called as moderator. So now we should find out that it can lose more kinetic energy in an elastic collision. Okay, see, the initial kinetic energy of the neutron is given by K1 I is equal to the initial kinetic energy of the neutron, that is K1 I is equal to half m1 v1 I square. Isn't it? And the final kinetic energy K1F is equal to half m1 v1F square, that is also equal to 1 by 2 m1 into m1 minus m2 by m1 plus m2 whole square v1f whole square v1I whole square. Okay. So, while the fractional kinetic energy gained by the moderating nuclei, that is K2F by K1I, is moderating energy which is gained by the nuclei is K2F by K1I, that is given by F2 is equal to 1 minus F1, that is elastic energy, which is given by 4 m1 m2 by m1 plus m2 whole square. For deuterium, that is m2 is equal to 2 m1, that is we should consider the mass a little above than the mass of neutron. We obtain f1 is equal to 1 by 9 and f2 is equal to 8 by 9. If you consider m2 is equal to 2 times of m1, and if you substitute that in the equation, that is the fractional kinetic energy F1, which is given by K1F by K1I. That is M1 minus M2 by M1 plus M2 square. Then we'll get the value of F1 as 1 by 9 and the value of F2 as 1 minus F1, we'll get it as 8 by 9. Okay. Almost 90% of the neutron's energy is transformed to deuterium. For carbon, F1 is equal to 71.6% and F2 is equal to 28.4%. In practice, however, this number is smaller since head-on collisions are rare. If the initial velocities and final velocities of both the bodies are along the same straight line, then it is called as one-dimensional collision or head-on collision. Okay. In small spherical bodies, it is possible if the direction of travel of body 1 passes through the center of body and 2 which is at rest. They both travel in the same straight line after the collision. In general, the collision in two-dimensional where the initial velocities and the final velocity lie in a plane. So let us consider the collision in two dimension. So as we saw in the previous figure where mass m1 collides with the mass m2 which is at rest, okay, it depicts the collision of a moving mass m1 with a stationary mass m2. In that case, linear momentum is conserved, and since the momentum is a vector, this implies three equations for three directions, that is x, y, z. Okay, consider the plane determined by the final velocity directions of m1 and m2 and choose it to be xy plane where they move after the collision. We consider that plane as an xy plane. The conservation of the z component of the linear momentum implies that the entire collision is in the xy plane, and the xy component equations are given by m1 v1I is equal to m1 v1f cos theta 1 plus m2 v2f cos theta 2. Okay, and the another equation m1 v1f sin theta 1 plus m minus m2 v2f sin theta 2. So here v1f, v2f, theta 1 and theta 2 are unknowns. If theta 1 and theta 2 are 0, then again we get the equation that we got for one dimension. If further the collision is elastic, this is for completely inelastic. If you consider the collision as elastic collision, then we get the equation that is half m1 v1I square is equal to half m1 v1f square plus half m2 v2f square. Okay, this is the equation. So now let us consider a simple problem. Consider the collision which is depicted in the figure. So this is the figure. Consider the collision which is depicted in this figure to be between two billiard balls with masses m1 is equal to m2. The first ball is called the cue while the second is called as target. The billiard player wants to sink the target ball in a corner pocket which is at an angle theta 2 is equal to 37 degree. Assume that the collision is elastic and that friction and rotational motions are not important. So here you should find out the value of theta 1. Okay, that is the question. So coming to the solution, from momentum conservation, since masses are equal, v1I, the initial velocity component, is equal to v1f plus v2f. Okay, and v1I square is equal to v1f plus v2f multiplied with v1f plus v2f, isn't it? So we can write it as v1f square plus v2f square into 2 v1f into v2f. Okay. So since they have given, he wanted to sink the target ball in the corner pocket which is at an angle of theta 2 is equal to 37 degree. So we can write it as v1 f square plus v2 f square plus 2 v1 f v2 f cos theta 1 plus 37 degree. Okay. Since the collision is elastic and m1 is equal to m2, it follows from conservation of kinetic energy that v1 I square is equal to v1 f square plus v2 f square. So comparing these two equations, equation 1 and equation 2, we get cos theta 1 plus 37 is equal to 0, and theta 1 plus 37 is equal to 90 degree, and theta 1 is equal to 53 degree, isn't it? So this proves that when two equal masses undergo a glancing elastic collision with one of them at rest, after the collision they will move at right angles to each other. Okay.